All right, so for the first one today, we're going to welcome Kent Nebergall, where he's going to talk about settling Mars while protecting science and exobiology.
I suppose I should say good evening, ladies and germs, given. Anyway. So one of the topics that's been coming up and was just talked about in there was lithopanspermia. In other words, the idea of life being moved from one planet to another when a meteor hits. Or as I like to say, if a meteor loves a planet very much, it tends to spread things out a bit. But litho is, of course, rock. Panspermia means moving from one place to another. We're talking exclusively about lithopanspermia from Earth to other planets for this talk, because we're 100% certain life is here. Doesn't always seem like it, but there you go. What's the implications if we find life on Earth, life from Earth on Mars for astrobiology and so forth and settlement? So there's been some very good studies recently. This is from a bunch of people at NASA and the European Space Agency on this subject. And apparently it's not just the solar system. We have mechanisms that can move. There we go. If we toss stuff out from Earth, and there's a lot of evidence the late heavy bombardment around the time life formed would have kicked stuff out all across the solar system. But if it gets close to Jupiter, it can actually be ejected into interstellar space. And it can be ejected for literally thousands of light years. So depending on the speed, I just did napkin, spreadsheet math here, meters per second, kilometers per hour, light years per eon, or million years. So their study said about 2,000 light years. That circle is to scale at 2,000 light years across. So pretty much every star you see in the night sky could, if we find a signature of life in that spectra with the James Webb Space Telescope or something like that, there's a possibility that's from Earth. You look at the night sky and you see all these places and you think, is there life out there? Maybe. What's even weirder is it could be from what is now New Jersey. If we find it more spinward, it could have been tossed ahead of us as the galaxy rotates, because we've rotated 4 times around the galaxy since life formed. Or if it's more backwards, then it could be from Earth. If it's off in the dead zones there, it's probably not from Earth. But of course, it's always more complicated than that. That's the bad news. The good news is the Europeans conveniently launched a wonderful space telescope called Gaia a few years back that's already returned 2 data sets, and it's plotting the exact position and velocity of every star that can be seen readily with, so basically every star you can see with a decent telescope in the night sky, they've got velocity vectors for it. They've already returned 2 of the 3 data sets on the primary mission. So if we find something with James Webb or a future telescope that has a life signature, we can use this data to play the clock backwards and see if it's ever been close to Earth. And they actually said that in the original paper. That's not an original observation from 10 years ago. So what are the implications for Mars settlement? There's a high probability of Earth microbes there. Whether there's indigenous life or whether it came here is irrelevant. There's a high probability of Earth life there anyway. If it can get to the edge of the spiral arm, it can get to Mars just fine. Also, we should look at it in isolation. We already have isolated habitats on Earth. Like Vostok in Antarctica has been separated from the surface for roughly 50 million years. So they've drilled down and they've set up systems to take samples from that are not contaminated from the surface. So as far as biomarkers on Mars, this is kind of just a quick scorecard. We've already found everything on the left column. We just found liquid water at the South Pole. So this is just kind of where we are in that whole survey in one slide. In terms of the basic principles of how we do things there now, when we send a lander, we sanitize it, but we don't sterilize it because it's up in this dead zone on the surface that's already been sterilized by ultraviolet radiation and by galactic cosmic rays, down to about 4 meters. However, when you get into one of the other implications of that study, if a rock has a depth of 3 centimeters, bacteria could be preserved 15 million years, and this is the various depths and so forth. This is actually based on a study the Japanese took samples of clay and other materials and put it on their exposed platform on the back, and then saw how long life would survive in Earth orbit based on the radiation from below the Van Allen radiation belts and so forth. So this is somewhat shielded from that, but it gives a good indication of that. The thing is, if we bury bacteria on Mars up to this depth, that's around the time the sun gets hot enough that Earth will not sustain life. The oceans start boiling at that point. So Mars will be terraformed whether we are involved or not, because the sun will do it for us eventually. But this also means that if some of our original plans for settling Mars, we thought, well, we'll dig 5 meters down because that'll be protected from galactic cosmic rays for our inhabited capability. Anything we leave down there is going to stay down there. So what does that mean? Well, if we take a low-risk approach, in other words, we don't find any evidence of life whatsoever, we can still probably go down 4 meters just fine. We can set up our habitats and domes and so forth. We can have autoclave airlocks to do sampling below that level with robots and so forth. If there's a high risk, we just stick with the surface dust that's been kicked up and sanitized every Martian year for billions of years, every time that there's a sandstorm or dust storm. That's been cooked by UV. It's as sterile can be. And it's fairly simple to extract dust off the surface. We can still use craters for our habitats. We're just a little more protective, and we tend to focus on using water shielding instead of regolith. So 2 near-term technologies we'd want are some of these ice domes that we've seen a lot of recent studies on. That's a much more logical solution if you don't know if there's life on Mars. And mining of dust off the surface, which we don't really want around anyway because it tends to get kicked up by rocket exhaust and so forth. This, of course, we can also use on the moon. So we're going to use atmospheric extraction because you need it for fuel and so forth. We can get ice and water from underneath the surface and dust mining. We can kind of focus on these in the near term, and then if we get a chance to work on these in the future on the moon or with conditions on Mars, then we can expand in those directions. So the ideal site for human settlement, we would want an old crater because of that history gradient. The older the crater, the longer it's been exposed to radiation. The longer it's been exposed to radiation, the more play you have in the subsurface between when it's biologically active and when it's sterilized. So if it's a 15 million year old crater, you've only got 3 centimeters. But if it's a billion-year-old crater, you've got 3 meters before you have to worry about your foundations hitting something. If they're full of dust, that's kind of a bonus. We've got more material to work with. Water resources, this mid-latitude glaciers that we found of nearly pure ice with just a few layers of dust on top, absolutely perfect for this. All you really need to do is filter it and sanitize it when it comes up, and you're good to go. And then, as we said, surface domes with ice. If we find life, we would want to, of course, filter it at the water at the molecular level so that there's no chance of biological contamination of our habitats or whatever. Dust mining, of course, it's very simple to do. You just run it through past a magnet. You can extract off the ferrous materials, run it through an electrostatic separator, separate off other metals, and then on down the line. You don't have to grind up the rock at all. It's already ground up for you. And then rock mining, I think igneous and metamorphic rocks, because they're treated by heat prior to that point, are probably relatively safe. But anything with metal deposits sedimentary, as long as you're sterilizing robotic equipment and not physically coming near it, I think you're cool there as well. If we find life and we find a genome, we would want to examine its genome and so forth like that. We could, theoretically, have sort of a Martian Jurassic Park where we put everything in a test tube, essentially, that is able to simulate the conditions of ancient Mars. And we can do that in a space station, not on Earth orbit, but in maybe Mars orbit or something like that. The other thing we could do is wherever the sample is, as long as we don't introduce the sample to the stuff that we have to maintain, if it's a separate pod, then we can basically move the sample to another pod, sanitize the equipment from any Mars microbes, do any work on it, sanitize it again from any Earth microbes, and then it's ready to go for the next time. So we can basically have a revolving lab where we're able to maintain our equipment independent of our samples. So like chasing the mice from one cage to another when we're doing work in labs on Earth. And then preserving other science, whenever we're doing this mining with ice, we would want to do radar surveys, we would want to do samples along the way. Anything that goes through a filtration system, we would want to preserve exactly the depth and location where those samples were, and then examine the filters. You know, check the lid screen, so to speak, for any microbes or whatever that you're finding under the surface. Because scientifically, the H2O that is pure H2O is not that scientifically interesting. It's the stuff floating in it that's interesting. And then finally, minerals and metals. We would want to do core samples as we're going along and preserving those, same way that archaeologists will preserve samples of different digs for future generations. We would want to have a library of that information, and we would want to distribute it around the globe so that if we mine out an entire valley of something, we would want to have all that science that was there before we ever showed up in a place where future generations of scientists could examine it. So just a simple animation if we were doing a strip mine in theory. And this is also true with asteroids, this is also true with the moon, where there's no biological component, but we still have a scientific component. We want to know how these asteroids formed and so forth for future mining, if nothing else. There's a monetary value to this as well as a scientific value. So we would go through, take some core samples, scan it using whatever technology is available, sort of like a CAT scan or a PET scan of the rock to get a three-dimensional cross-section of it as in its bedrock state. And then we would do the next cut and move on from there. We don't want to throw away all those wonderful bits of information when we're trying to extract the atoms for our settlements, because they are both valuable in this situation. And then, so what are our open questions? If we don't find life on Mars, then we think it's very difficult for lithopanspermia to be a viable option. That means we're underestimating the amount of damage that biology takes from galactic radiation and so forth. We're less likely to find life on Europa, Titan, and Enceladus unless it's indigenous. It's probably safe to move into lava tubes, things like that, and then it just opens things up for things like tourism. If life is found, then we have a good probability measure of, okay, how many of those rocks could have been ejected beyond the solar system or into Titan, Enceladus, and so forth, and what are the likelihood of life being found there. We're also, if we find life, we would probably still do virtual reality tourism or telepresence in those areas that are considered too biologically active for ready access by humans. So just a quick timeline of what's coming up here. The ExoMars rover in 2021, which should go about 1 or 2 meters below the surface with its drilling rig specifically to look for past or present life. James Webb Space Telescope, currently 2022. And, of course, the big Falcon rockets in 2030 approximately, or sooner. So that's about it. Any questions? Yes, James?
You mentioned James Webb Telescope. Have they moved it to 2022?
That's the last number I've got.
Really? So not March of 2019?
No, it keeps slipping. Yeah. I know you want I know you want a space telescope named James.
You want to see it before you
But every 26 months you just go,
Okay.
So, I can't remember if you mentioned it, but when was the last time significant rock stuff blasted off Earth's surface? How long ago was that?
Probably when the dinosaurs died, but I don't have. Somebody could have calculated, because there's enough evidence of what was the impact velocity and all that. I didn't want to talk to that because I don't have that data. Their study, this is worth mentioning, their study was focused on life appearing around the time of the late heavy bombardment and all the, tons of meteors that came in at that point. But their theory was that it would have kicked off roughly 1 billion rocks that would have been viable into interstellar space. But any stars that would have been close enough to have been fertilized in that way would have been within the same nebula that the Earth formed, because we would have still been in that nebula that early. So it's interesting to think of life forming on the surface of the Earth at the same time that everything around the sky looked like the Orion Nebula. But the flip side of that is that if we take that Gaia data, life or no life, we could theoretically run the clock backwards and figure out where our nest mates were, if we can find any of those in the sky. It's like this star and this star and this star were from the nebula where our star formed. So that's an intriguing idea in its own right.
But the variable is velocity.
Yeah.
It goes to this star versus this star.
Yeah.
1/3 the velocity.
Yeah. So it could be anywhere in between. Yeah. So.
Has anyone taken something like what is Deinococcus radiofurans and put it like a meter under frozen ground, like a Mars simulator, and get some radiation or anything to see if there are any Earth organisms that can? Deinococcus radiofurans is the one they found living in nuclear power plants. They can take it.
Oh, I see. That's kind of what that study was with the Japanese, is that they wanted to put it in space because we cannot make a particle accelerator anywhere remotely as powerful as a cosmic ray, or a really hard cosmic ray. Funny thing that happened when we were getting ready for this, my 4-year-old son came home from daycare with a bunch of rocks in his pocket, and he said, we should take these rocks in the backyard and we should plant them and we should put sugar on top of them. And it's like, where did you get that idea? It's like, it's my idea and it's a good idea. And, because he's 4, and I was like, oh, that's cute. And I kept one of the rocks and I put it on top of my cabinet just to remind me of that little cute moment. And of course I did as all parents did. I immediately took out my phone and had him repeat the story. But when they did that study with the Japanese thing, they found a 20% survival rate in normal clays. But if they added glucose, it was 85%. So I thought it was a good idea. And someday when you're a famous scientist, I'll have to break the news to you that the Japanese did prior art on your discoveries. So anyway, any other questions? Yes?
Is your assumption here, or your premise, that it's more likely that if we find life on Mars, it would have come from Earth, or as opposed to original genesis on Mars?
The idea is basically that it's all one big happy family one way or another, because we have 100, I think Zubrin says something about 100 kilograms of rocks from Mars per year raining down on Earth now. So if there's enough cross-contamination to go from the high-gravity well of Earth back to Mars at this level, and there's enough coming back the other way, then, and it's to some degree interstellar. There's also, as I was wrapping this up, there was a study that there's probably thousands of asteroids in the solar system that are captured from other solar systems. So it's all one big ecosystem. It's a fragmented ecosystem, the way that Australia is fragmented from the rest of the world, but it's got a component of commonality that is vast. So we can't assume that everything is a sterilized test tube, the way the planetary protection people are thinking, that this is a completely sterile object. No, it's not. The bacteria got there a long time before the humans ever existed. So one way or another. So I'm just backing up that assumption that even if we find no life there that's indigenous, or if we find whatever, it's almost certain that there's Earth life that's reined in at some point or another.
But it would seem, that's certainly a possibility, and that may be the way it is. But it would seem that as part of the scheme here, we would want to find, if we found life on Mars, we would want to first of all see if it was in any way similar to Earth, that it either could have come from Earth or went from Mars to Earth.
Right, and it would be isolated, but also the factor is that the bacteria within an energy supply does like as much evolution in a week as multicellular life has done since the beginning of time. So it's because of the generation rate and so forth. So there's probably a fair amount of diversity, but bacteria is still bacteria. It hasn't really shifted out of that except for certain levels. So we would probably examine its genome, see if there's any interrelation, but there's probably will have been, layers of Earth life, Mars life, Earth life, Mars life that have interacted before humans ever existed. That's my point, on both worlds.
Let me try a thought experiment about that. Let's say you want to go to Mars, drill into an underground frozen aquifer, find some ancient bacteria, analyze their chemistry. There's something like DNA, but it's not quite DNA. It uses a different sugar to ribose. The codons are differently organised. They're not even triplets, they're quadruplets. Transcription enzymes are different. There's a completely different set of amino acids making the proteins, and they're a mix of dextro and ribose.
You made your point. So what's the question?
Is that a true second genesis that's independent?
At that point, it's highly. That's a good question. At that point, it sounds like a second genesis or the equivalent to one, because something would have went very, very, very differently if you're going, RNA to DNA is one thing, RNA to, and we've had, God knows how many examples since the Earth formed. We haven't had a non-example of that. So at the molecular level, if you're getting that far off the line, even if it originated on Earth, went to Mars, got a foothold there, and got wiped out here, it's still effectively a second genesis from a biological standpoint, whether it was indigenous to Raj or not. It's sufficiently different at that point to be interesting, and it would be impossible to intermingle it back necessarily. We could see 1,000 years from now, you could have a civilization that takes different samples of this stuff and then figures out how to genetically engineer life for new habitats based on not just the palette that we have on Earth, but a wider palette of life that may be from Earth, whatever, but that has a broader foundation scientifically for the engineering.
Interesting, though, wouldn't it?
Yeah. Actually, I think that's the plot of the new Predator movie. Yeah. Sorry, you had a question?
If Panspermia had occurred from outside the solar system and started on Earth 4.7 billion years ago, and it had also started on Mars at that time, was Mars developed enough with the water environment, and how far along would the evolution of Mars?
Well, at some point, it's like the idea of life forming in other planets, in other solar systems that have way too high a gravity level, or they're covered with oceans like they're recently discovering. It's like, okay, you could have really advanced dolphins, but they're not going to develop fire necessarily under a giant ocean. And even if they find an island and grow arms and legs and so forth, they're not necessarily going to get out of that gravity well very easily without
I'm just thinking in
nukes.
terms of 4.7 billion years to when Mars. I don't know enough about Mars to know when it dried up. So how long in the evolution compared to Earth?
The speaker today had probably a more informed opinion on that, and I tend to agree with it, which is probably stromatolites and some other.
That was the beginning.
Yeah. Well, it's the earliest fossil record. I've actually got a highly polished stromatolite from Australia it's like, this is life from a billion years ago.
From the old
Yeah.
original stuff.
Yeah. It's beautiful, too. Ironically, it looks like a little planet because it's all layered. So it looks like gas layers and so forth. We're down to 5 minutes. Any more questions? Is the next speaker here? Okay. All right. Well, I'll let you get set up then. Thanks so much.